So what is the statement again? The statement is that if I look at all of the cohomology groups, and this is all mod 2, all of the cohomology groups of symmetric groups together, this is fruitful because this forms an object. So this is the free. Oh, and let me do one thing. Let me make this smaller. It's the free primitively generated in the standard sense of that word. Some of these things we'll have to define for you. So it's free primitively generated. In component, that's going to be the simplest thing to. That's basically by almost by definition. In component, Hopf ring is the main part of the structure. Or sorry, divided powers. One more adjective. Hopf ring. Generated on just a quote unquote handful of classes. On the 2 to the ith symmetric group, there's a class in degree 2 to the I minus 1. And those few classes across symmetric groups, not every symmetric group supports a generator, just the ones that are powers of 2, and those ones generate all of the cohomology. So let's just take the different parts of this definition one by one. So what does it mean to be a Hopf ring? Well, we had a lecture on that. It's a ring object in coalgebras. We did a few calculations. So for those who are watching in video, you can go back to Hopf, the homology of Eilenberg-MacLean spaces. So in this case, so that means you've got 2 products and a coproduct. So this is just going to be the ordinary cup product. 2 products, 1 coproduct. This is going to be the ordinary cup product. And we're going to define as 0 between components. And that's exactly what's meant by in component. So let me just point that out. That's the definition of in component. It's a coproduct of rings, you could say, if you want to be fancy. The other thing that's easy, familiar, is the coproduct itself. And this is dual to the product that we used to talk about the homology last time. So this is the, it comes graded because I'm taking this direct sum. And then this is induced by, well, if you're algebraic, you want to say it's the inclusion of BSN cross SM into BSN plus M. Or if you're geometric, you want to think about unordered configurations of endpoints in an infinite dimensional box. And then if I have M of those, I can stack them next to each other and I get N plus M such configurations. That way gave us a product on homology, but gives us a coproduct in cohomology. And then finally, the less familiar character is the second product, the additive product, which we call the transfer product, because so I'll even point out that it is defined even in finite dimensions. let me make this RD, use the, well, so if I have, there's a space that let's just call conf n comma m ID, where these are bicolored configurations. So we're used to fully labeled configuration. Every point has a number between 1 and m. We have unlabeled. Every point has, no point has any label. They're all identical. These are closer to that. The labels are just 0 or 1, or we can think of this as color, it's red or blue. And then this is just sort of forget the labeling. So these are labeled with 0 or 1, say, and then this map is forget the labeling. Or no, sorry, forget, or just remember the 0 points. Sorry, the map down is forget the labeling. We remember the 0 points or the 1 points. So this is really an inclusion. Here, the 0 and 1 points on the left-hand side are allowed to overlap. On the right, they have to be distinct. And now we forget the labeling, and we've got unordered configuration of n plus m points. And then what we can do is, given a pair of cohomology classes in these unordered configurations on the left, we can pull them back and then take the transfer of this. This is a covering map. Let's call it P. Let's call this I. So what this is the transfer product is just P upper star. We're using the Kunath theorem, or sorry, I upper star, composed with the transfer for P. And remember, the transfer is the kind of thing that if you've got these tome classes, you're just taking their image because you've got a proper map. And so in fact, that's the way I like to think about this. Let's look at this diagram again. If I've got a W mapping here, and I'm thinking of the tome class, and then a V, well, I'm just looking at their pre-image, that's really W cross V, and then I take the transfer, and what that really means, if, so there's really sort of, the submanifold defining things is quote unquote the same. What this means is that if we think of W and V as conditions, W is a condition on endpoints. Remember, for example, 2 points in the configuration, it's unordered, but if they share a coordinate or 5 coordinates. And same for V on M points. And what I can do is then make a condition on N plus M points where I say this condition is satisfied if I can break up my N plus M points into a set of N and into a set of M, such that the first N satisfies the condition defined by W and the second M satisfies it defined by V. An important point, and something that we'll probably come back to next time more, is that I'm allowed to break up my N plus M points in all possible ways. So I could satisfy this multiple times on the same collection in this space here. So it's a way to make new conditions out of old, formalized by this transfer product. We're of course looking at D equals infinity. In that case, it really is, alternately, this is, alternately, and this is the original point of view of Strickland and Turner. This is something that I rediscovered and thankfully gave a talk in Sheffield, and Neil was able to say, hey, I know what that is and I've written about it. So alternatively, the inclusion Sn cross Sm into Sn plus M, any inclusion of a subgroup H into G gives rise to, well, the map from BH to BG is a covering map. And so, and because what you can do is really think of BH as, these are finite, so this is, we can think of BH as EG, which H will act on freely, mod H, and so, and BG is EG mod G, and so this is a further quotient. And so, so this is a covering map. The natural map on cohomology goes back this way. So on cohomology, this map is our coproduct, but I've got a transfer map, and that's our product. So that's this structure. It's a second structure. As I'll say in a little bit, it's related to things that representation theorists have looked at for quite a while. Let's give a couple of the axioms, because then we want to unpack them. So we want each product, because this is a Hopf object, everybody in the world is a bialgebra. This is easy because cut product is induced by the diagonal, and this is and the coproduct is induced by a map of spaces. So it's an easy diagram chase. This is also a bialgebra. And that's harder. And again, we'll have to come back to some of these facts. And it's really, maybe it's harder. It's not too hard, but it's also a special thing about symmetric groups. And then there's this distributivity, and let me remind you, because again, we discussed it a bit with Eilenberg-MacLean spaces. Hopf-ring distributivity says that if I'm taking a cut product with the times product, the multiplication product of something and something else, which comes as a plus product, an additive product of two elements, then I can sort of, I know what that is inductively, or I can, I have a relation depending on your point of view. I'm going to look at the coproduct, and I'm going to distribute over that. So I'm going to look at the sum over, I'm going to call the coproduct, break it up into the tensor product like this, and I'm going to take each of those things which appeared in the coproduct, and I'm going to multiply them by B and C through the cut product, and then I'm going to take the transfer product or the plus product between them. So you're distributing the plus product over the transfer product, but you have to do it through the coproduct. So that's exactly what it means to be a Hopf-ring. There's one other, two other conditions. Well, primitively generated is the usual thing. So these gamma i's have no coproduct, effectively no reduced coproduct, just the sort of trivial coproducts. And then there's this divided power operation, and again, I'm going to have to defer it until we develop some other aspects of Reith products and things. But let me just say, if before we made a new condition on n plus m points using separately those conditions on n points and m points, and so that's a union of conditions. So if this is the sort of a union of two distinct conditions. Then divided power is the repeating, or the union again, repeating of a condition. The point is that, and here's the thing, because there is a divided power operation, so this is the divided power for the transfer product, that means that, so the standard in algebra, divided power means that then you've got that the transfer product of something with itself is going to be, and here's a funny thing we're going to do, we're going to denote the divided power through subscripts. So for ease, clarity, non-crowdedness of notation, the divided power operations are given by subscripts. Okay, so that gets us all of the structures. Let me say one more thing before then unpacking how this looks for cohomology of symmetric groups. It's an important analogy to keep in mind. So related example. And this is something that was partially noticed by Zelevinsky, representation theorist around 1980. And that is, if you take the direct sum of representation rings, and I could do this over any ground field I want, of symmetric groups. So look at all the symmetric groups together. This is a Hopf ring. Zelevinsky only looked at part of the structure, just a Hopf algebra, where, consistent with the notation above, this is the internal tensor product. So this is the one that's internal to a single rep S in. And the other thing is, it only works if you say it's zero between different symmetric groups. Let me do one other thing. Okay. Then what about the coproduct? The coproduct is basically restriction to S in cross Sm. Same, and then I can take the direct sum of those maps. And then this other product is a more familiar character. And sometimes we call, in the symmetric group case, instead of transfer product, I might call it an induction product, because what you do is you take some V and W. I'm going to look at their, let me do this below. I'm going to take their external tensor product, and I'm going to induce up from, this is naturally a representation of Sn cross Sm. Of course, that sits inside Sn plus M as a subgroup, and so I can induce. And if you think about it, there's sort of double cosets, and you see exactly the covering kind of covering space transfer formulas are the same here, and I'll comment. This is not. This is in fact can be viewed as a special case of the Strickland-Turner theorem plus the Atiyah-Siegel completion theorem. Okay, but let's not get too far on the general story. Let's now unpack what this means. And let me venture back up on the board. So let's just see what this means calculationally. Let me say one other general fact, though, that's key, is that in a Hopf ring, oh, by the way, this is maybe technically a Hopf rig. I'm not going to use the negatives. They are there in this case. There is an antipode, but we don't need it. It's basically the identity, if you will, because the transfer product is exterior. In any case, Hopf ring distributivity, if you think about it a moment, if I apply it again and again, implies a spanning set and thus a basis of the form M1 transfer M2 transfer dot 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 transfer MK, where each MI is a monomial in the times product. Okay, and this is essentially the same as reducing in a regular ring. Every element is a sum of monomials. Here, every monomial is a sum of these special monomials. So it's no more nor less than applying distributivity again and again. So now let's understand what the statement that we made on the left implies for the cohomology of symmetric groups. So we're going to take symmetric groups one at a time. I'm going to go down below, give myself a little room. Maybe I'll give myself even a little bit more room. So BS2, well, oh, I think I forgot to say there's always the unit class. But BS2, there's only one class that we named, which lives on BS2, that's gamma 1. And then I can take gamma 1 squared, gamma 1 cubed, and so forth. And it's really just the cohomology of RP infinity. And again, let me just say I've also got the unit class in degree 0. And so it's the cohomology of RP infinity, our familiar friend. But that's a good place to start, and then talk about BS4. Now BS2, BS0, there wasn't anything. BS1, there wasn't anything. By the way, we only look at even symmetric groups because we're doing mod 2 cohomology, and some basic facts about CELO subgroups that I'll emphasize even more next time say that the even and odd have the same cohomology, the odd symmetric group having the same cohomology as a previous even one. So we'll go to BS4, and in degree 0, we'll still have something that we'll call 1, 4. Now, in degree 1, I can take gamma 1 and transfer product it with this 1, 2. In degree 2, I can take gamma 1 squared and transfer it with 1, 2. I could also imagine that I've got gamma 1 transfer gamma 1, but this is divided powers, so that's 0. So really what I want to say is I have gamma 1 divided power 2, and that's happening in degree 2. In degree 3, I have gamma 1 cubed, transfer 1, 2. I can also take gamma 1 squared, transfer gamma 1. This is non-zero. Those are distinct classes that I'm transferring together, and so forth. It'll grow as you would expect these particular classes. And again, here, I can't really take gamma 1 squared, transfer gamma 1 squared. I really have the divided power there. But on BS4, we also have this class in degree 3 called gamma 2. Okay, And eventually I'll have, say, gamma 2 squared, et cetera, et cetera. The Hopf monomial basis says that I really only need to consider these two things. I do have things like, I should be clear that I am going to have gamma 2 times gamma 1, 2. That ends up being non-zero. We're going to talk about relations and multiplication in a bit. But in the meantime, let me just say, because I much prefer this, that there is a graphical way to see all these classes. So on the first column, so the unit classes are not so interesting. In the first column, I'm going to use 1-by-1 blocks. The reason that I care about the size is if I keep track of it, then we get that the degree of a class is equal to its area. So now over here, I can try to, let me erase some things that are 0. I might need to space things a little bit better. But over here, I, for example, will denote this transfer product by juxtaposition next to each other. So, okay. And we also said that there was this gamma 1 divided power 2, and for reasons which will become apparent later, gamma 1 transfer gamma 1, I'd have a solid line here. I'm going to put a dashed line for the divided power. These classes, we'll try to fit them in, are represented by pictures that look like this and this. And this is a new class. It's in degree 3. So we'll give it total area 3. So if these are width 2, this would have height 1.5. I mean, it doesn't, you don't have to do the diagrams like that, but I prefer that. So when we take this cut product, it will be represented by stacking. So cut product is always stacking over. So I'm going to put this gamma 1 divided power 2 on top of the gamma 2. These look as you would expect. 1, 2, 3, 4. 1, 2, 3. And this is 2 of those with the perforations in the middle. Okay, so you can actually, you've got something like Young diagrams, except now I've got a couple different sizes of blocks in front of me. And this gives an additive basis, and we call this the Skyline Basis. And it's takes a little bit, but not too long to get to translating between them. So I'll give different elements. Let's see. Let's first think about what gamma 1 cubed transfer gamma 1 squared transfer gamma 1 looks like. And let's also think about, conversely, let's think about what this class looks like. This class is in algebraic notation. Well, this would mean I've got a gamma 1 cubed, that's a 3 column. Gamma 1 squared is a 2 column. Gamma 1 is a 1 column. This says I've got this new larger block. That was my gamma 2 with the other block stacked on top of it. That was gamma 1 divided power 2. So this is gamma 1 times gamma 1 divided power 2. And then I've got this empty space, and those empty spaces are transfers with units in cut product cohomology. So we can keep going. Let me just say that for BS8, we get, let me call attention to, now you could have non-trivial non-trivial transfer products of things that live on BS4. So you can, for example, take that would be gamma 2 squared, transfer gamma 1 divided power 2. But you also have a whole new set of, you have a whole new generator, gamma 3. That's just going to be another, that's a Hopf ring generator. It's primitive. It's going to be a solid block, 4 wide, and wanted to have area 7, so it's 7/4 high. And it will form a polynomial ring. The things that sort of stack nicely on it include, this will be an important subalgebra, include this now gamma 2 now has a second divided power. That's this 3 block now repeated twice. And gamma 1 has a 4th divided power. And so those are sort of new classes. Everything else, those are indecomposable with respect to the transfer product. Everything else will be made up of smaller columns. So that's another way to say what's going on. You've got single columns. Those are the indecomposables on symmetric groups that have 2 power indices. And then those columns can be transferred together to make more complicated skyline diagrams. Okay. So that's what the basis looks like. And I want to call that, I wanted to say now, and I'll probably emphasize more next time, that this is naturally, the basis decomposes here in a way similar to our basis for homology. So this ends up being dual to, I'll put that in quotes because this is not, this is about a pairing, and I haven't told you about the bases, and but this ends up being dual to Q3 star Q2 star Q1, whereas this one here, it's much more subtle, but I'll give you a preview, is dual to Q1 2 star 1 2. Okay, so that's the basis. The more interesting thing, the very interesting thing is that we can now understand cut products. And I just want to focus on BS4 for the moment. So let's just talk about the cut products. The cut products on BS4. So what about, say, this class times this class? So that is, let me get back over here. So what is that? That's gamma 1. Let me write it the other way. So this is gamma 1 divided power 2 times gamma 1 transfer 1 2. So in Hopf ring distributivity, this is my A, this is my B, this is my C, right? So I need to take the coproduct. Well, it's a primitively generated divided power object. So then the coproduct of gamma 1 divided power 2 is, well, gamma 1 divided power 2 tensor the unit for transfer product, which it lives on BS0. It's kind of a formal object. BS0 is a point, but then I also do have gamma 1 tensor gamma 1. That's what happens in divided power Hopf algebra. And then I've got 1 0 tensor gamma 1, 2. And so I take the sum. So this is going to equal the sum, and the first term would be gamma 1 divided by 2 times my b, which is gamma 1. And I have to take transfer product 1, 0 times my c, which is 1, 2. But these live on different components. And in fact, that will happen in general. In this case, because it's an incomponent Hopf ring, I could just specify that we only need to take coproduct over into the components that B and C live on. And so really I can just focus on this gamma 1 transfer gamma 1. And then what I have is I'll have gamma 1 squared transfer gamma 1. Okay, so graphically, this becomes this equation, this equality. And you start to find, I think I'll be more and more brief as we go along. Let's next do this times this. And again, there's only one coproduct, so the coproduct ends up being break up along columns. Now, this transfer product is commutative, so you're not respecting any order. So the coproduct involves both a 2 high tensor 1 high and one high tensor 2 high. And remember that well, each of these is coming from BS2, so it's just the cohomology of RP infinity, and we're denoting the powers of this class X, which we're calling X gamma 1 by stacking. So in the end, we just get what you see when you stack that block on the first column. And then there's a subtlety, because it looks like you should get something like this. If we go through the definition, I get gamma 1 squared transfer gamma 1 squared. But again, the transfer product is divided power, so that's 0. So this is why we have to be careful with the little dots between the perforations, if you will, between some of the columns, because we find that so the distinction to make is that this equals 0 with a solid line between it, because it's representing a non-trivial transfer product of a class with itself, whereas this is the divided power, kind of witnessing that that's 0. It is twice it is what is making that 0, if you will. Okay, let's give some more examples. What do I want to do next? Again, let's maybe just do an easy example. So and again, because column stacking is commutative, even though I end up with, say, this, what I'm doing is just sort of putting this here to get the first term. And if I put this here, I get the second term. And then I'm, like Young diagrams, I'll have the taller column first. So the transfer product is commutative. So the next one we should look at is this. So that's gamma 1 transfer 1, 2 times gamma 2. But we've already said that what matters is the 1, 1 component of gamma 2, and that's 0 because we're primitively generated. So this ends up being 0. So that's a relation in the cohomology of BS4. So in fact, the cohomology of BS4, I've presented it through this additive basis, and now we know how to multiply by, if you've got these two distinct columns that are width 1 each, then you can kind of match and stack. If you have this 3 block, then it only multiplies with other 3 blocks and other 2 blocks, and in which case you're also sort of matching and stacking just a single column. What that ends up being is just I only need 3 classes to generate everything, and then a deceptively simple presentation that this relation that we just discussed holds. So people see this and say, oh, okay, well, that seems like a nice ring. But I want to spend the rest of the time to convince you that things are not so nice. I mean, let me first say that the formulas, the Hopf ring distributivity, conceptually gets no more difficult. So let's do one more, and I'll even pause for a moment and let people sort of try to write it for themselves at home. First, as I write the pictures down, let's think about what these generators are named. Okay, well, you'll have to know. This is on BS8. Sorry, let me show the example. So what can happen here? Well, so we've got this simple gamma 1, 2. Yeah, so let's go ahead and give them their names. This is just gamma 1 divided power 2, transfer 1, 4. This is what? This is gamma 1 cubed, transfer gamma 1 divided power 2 times gamma 2, transfer 1, 2. And what do we get? Well, one thing that can happen that you sort of see is, sure, the 2 block can now stack on top of the other 2 block. So this is gamma 1 cubed, transfer gamma 2, gamma 1 divided power 2 squared, transfer 1, 2. But the other thing is it can split up. And one of its 2 blocks, because there's a non-trivial coproduct that splits up the gamma 1 divided power 2, one of its 2 blocks can lead and go there, and the other block can fit on the end. And then there's other terms that you can imagine. Maybe why doesn't that block want to? So if let's just sort of say where the gamma 1, 2 ended up. It can end up here, or sort of end up here, if you will. But why doesn't it end up stacked on top of the middle at all? Well, I have that gamma 2 there, and that has no coproduct. And again, it's these perforations. The perforations in these rules have to go all the way down for the diagram to split up there. Let me write in that this is gamma 1 to the 4th, transfer gamma 2, gamma 1 divided power 2, transfer gamma 1. Okay, so there's a bit more complicated example. The point is, this is all algorithmic from so proposition, I'll even call it, these skyline diagrams, these Hopf monomials plus distributivity which are represented in the skyline diagrams. And you can use distributivity plus the sort of column matching algorithm, give an additive basis and multiplication rules for the cohomology of all symmetric groups, but thus the individual ones as well. So we've given enough information to determine all questions about cup products. By the way, there's something else coming where we'll talk about Steenrod action as well. Let's see, let's maybe switch boards. So I want to bring in a parallel story here and make the point that Hopf distributivity can give rise in more subtle relations than just vanishing of products. So let me back up and say, so therefore, all relations in the cohomology of symmetric groups follow from Hopf distributivity. That's the conclusion that we can make from that previous statement, just unpacking the main theorem and saying, okay, what are its consequences for the additive bases and cup products? But Hopf distributivity results in more subtle relations. And I'm going to talk about a parallel story, and we'll see that it's not coincidentally parallel. In fact, I only realized it was parallel because topology says so. Namely, let's consider some classical rings of invariance. I'm going to take the first, well, you can see how this could be generalized, but I'm just going to look at two sets of variables and look at their symmetric functions. So we're used to, and in fact it came up in the cohomology of Grassmannians, to look at a single set of variables, look at the symmetric polynomials in them, and that's a polynomial algebra in the elementary symmetric functions. So you might think, okay, this is going to be simple enough. But if you don't know this story, it's actually a little bit, yeah, it's remarkably complicated. And I think still maybe not as well understood, sorry, as we'd like. So what I'm going to do is I'm going to use, we just had those skyline diagrams. We're going to make diagrams here to represent such elements. So let me just give you a couple examples. This is going to represent the symmetric polynomial x1 squared y1 plus x2 squared y2. So I should have started with my key that these are powers of x, and these darkened ones are powers of y. And the rule here is that stacking is just giving us a monomial through products. In the first column, it's the first set of variables, the x1s and y1s, and the second, it's the second set. So this is to be distinguished from this shape, which is x1 squared y2 plus x2 squared y1. Okay. And the fun thing is, you know how we had this weird match and stack product? Well, that's what the product naturally is. So product equals match and stack. So in this case, what would you get? If we played the same rules that we were just playing with the Hopf ring, I would see if I was taking the product of these two, 4 white, 1 black, and 1 black here, plus I would actually get, if I match them the other way, 2 white, 2 black, and then 2 white over here. Okay. And let's actually look at the 4 terms. If we take the product of, let's see, x1 squared y1 and x1 squared y2, that product, along with these two, would give me this term. Whereas if I take x1 squared y1 and then x2 squared y1, I get, let me just say, if I match them this way, I get this product. So that's a little calculation you can make. It's just a cute little way you can represent symmetric polynomials. And well, even in this case, so then if I take F2, just the n equals 2 case of this, this is a ring generated by, I will give a minimal generating set because I prefer symmetry. We've got this class, this class. These are your standard symmetric polynomials, sigma 1 and sigma 2 and x and y, if you will. But now we also have 2 more. Okay, and the relations are, oh, let's just call these just A, B, C, D, E, F. So the relations are A, B is E plus F. So I could choose E or F as a generator, but by having them both, then I have the EF equals A squared D plus B squared C. And this is minimal. So this is a very simple ring to define, but you start to get interesting relations, and this quote unquote gets worse and worse. And the point is that if I fix any number of variables, so if I take plus, I went back and forth, but let's do x1, x in, y1, y in, you know, etc. fix some set of variables, x, y, set of variables. Just easier to use this notation because the point is that I've got a fixed number of sets of variables. You can just think 2, and then I'm taking the direct sum over these. This is a, well, primitively generated divided powers in component Hopf ring generated by the standard elementary symmetric polynomials in each variable. Or actually, sorry, because I did the divided power, generated by just, sorry about that, generated by, you know, the first symmetric polynomial in each variable. So this is a case where, and the same is true for symmetric cohomology symmetric groups, which is why I bring this up. This is a case where the individual rings, you get longer and longer lists of generators and relations. It's quote unquote just combinatorics. When you put these all together, and I haven't told you what the Hopf ring structure is, but it's basically take something which is symmetric in invariables and invariables, multiply it. Now you know it's symmetric in those with respect to the subgroup Sn cross Sm, and induce up to Sn plus m. In other words, symmetrize over the cosets. You get this this very succinct description, which, like what I was just telling you about the cohomology of well, we just did one of the simplest examples, BS4. You get this this very simple description of what are ultimately complicated rings. So this arises, and we'll make this so the relationship to cohomology of BSN. If we have, let's let n equals 8. So in cohomology of BS8, we have classes that look like this. Sorry, let me show you. And then the last two, which would be, so this is entirely analogous. I'm just reading off those other symmetric polynomials, which give rise to a subring. Isomorphic to this, to the F2 adjoin x1, x2, y1, y2, s2. And there's a topological reason for these two rings to be related, the cohomology of BS8 and this ring of invariants, and that's one place that we'll definitely go next time. But I wanted to again just sort of bring this back together by saying the Hopf ring presentation is kind of remarkably concise. Ultimately, it gives rise to rings which are pretty complicated, and I will talk about also, as well as we talk about these rings of invariance. It may be that various other questions in representation theory, rings of invariance, other sort of structures when you're looking at things like symmetric groups, but also alternating groups, general linear groups over finite fields. These two products, a standard product and an induction product in the relationship, may hold some applications, might be good for some applications in algebra. Okay, let me stop there for the day for the lecture and take any questions. Again, as usual, first the questions that people don't mind being recorded, and then I'll stop the recording. You in the chat, or you can unmute yourself. Okay, well, hopefully that meant everything was clear. I'm going to